Complex numbers. Ready for me to nerd out again? Maybe even more? No, not more. I could never nerd out harder than on eigenvalues, but this might be the runner-up. And, a lot of the topics that you develop a certain appreciation or dare I even say affection for as you go through your math journey, some of them really are just the product of struggle of I just never got it, I never got it. And then one day you finally get it and you're like, wow, this is actually pretty great. That's kind of my story with complex numbers. I never really learned much about them in high school. Like when I took algebra and we were solving quadratic polynomials at some point, it was like, hey, square roots of negative numbers. Okay, cool, what else? And then in my third physics class, so like the waves and thermo class, uh, I was struggling so hard with all of the wave stuff because it was all like trig identities and I just I had no clue what was going on. I just muddled through by sheer math and guessing. And then when I got to my first quantum class, so very much the equivalent of MSE 242, when complex numbers were coming up again, it was like, "Oh, I wish I understood this because I could tell I was missing something important." And there was no secret to my success. One day it just clicked, and I was like, "Oh, that's what that is. That's how you do this. Oh, this is great." And I've just loved them ever since. And this is one of those rabbit holes that the further you go, the more you discover that there is to it. I have yet to explore all the depths of complex numbers. So they may be complicated, but they might actually not be complicated if you don't overthink them, but they are definitely complex. Now, this is one of those words that's ruined for me forever. Like I just am unable to like say complex like a normal human being when I mean something is complicated because in my mind, complex means numbers that involve square roots of negative numbers. Notice I'm not saying imaginary here. You've already heard my rant about that. Let's get to it. What are we looking at today? So, what complex numbers are, two different forms for writing them, Cartesian form and polar form. We'll revisit Euler's identity again, which came up the first couple days of class, but now it's back, and it will be back again, as the semester goes on. I want to introduce the idea of a complex conjugate. This is one of those things that I, just back to the previous topic, I really just did not get because I feel like it was never taught to me. I just saw it in equations all over the place and nobody ever gave me the recipe for doing it. And it's not hard to do if someone just like sits you down and tells you what to do. So I'm going to do exactly that. And then how to extract the magnitude of a complex number as well. We'll do a little bit of algebra, multiplying, dividing, that kind of business, exponentiation, and then just a little bit about dealing with complex vector spaces. Not a lot, but I just want to introduce one or two core ideas. So that's what's happening here. I am, of course, the square root of -1. If you want to get a little bit more mathy about it, then plus and negative I are the numbers that solve the equation x squared plus 1 equals 0. Now, of course, algebraically, this is just equivalent to plus or minus square root of -1, but many numbers are defined by their properties rather than their values, if that makes any sense. Like, for example, pi is not defined as 3.14 whatever. Pi is defined as the ratio of circumference to diameter for a circle. And it just so happens that that number has a value of 3 point whatever. Or E is not defined as 2.71828 blah blah blah. It's defined as there are a few different definitions for E, but one that I do like is that it is the exponential base that when differentiated returns itself. So likewise, to define what I what I am, I actually hesitated there for a second. That's going to be a problem. But I is the solution to x squared plus 1 equals 0. Now, where do these numbers live? Well, they're not on quote unquote the number line. They're not on the real number line. They are on a separate number line. But these two different number lines, the real and the so-called imaginary number line, they aren't parallel because they do intersect. They intersect at 0. So, as I've given away on the text here, how do you take two lines that intersect at one point but otherwise have nothing else in common with each other? They have to be orthogonal. They have to be at right angles to each other. And so this means that we can use these two number lines as basis vectors for a two-dimensional vector space. And this is what the space of complex numbers is. It's a two-dimensional vector space that has certain properties, and we'll look at some of them. And the basis vectors of this space are 1 and I. We can build any number in this space with a linear combination of 1's and i's. So the complex plane then looks like this. It's got a real axis, it's got an imaginary axis, and I've just labeled here several different points in the plane just so that you can see where they live geometrically and how we label them. So by convention, we write the x coordinate, if you want to think of it that way first, and then the y coordinate. So the real and then the imaginary part. And this is our complex plane. Now, for writing things, oh yeah, that was the other point here I wanted to make. For writing things in Cartesian form, then we really are just doing horizontal component and vertical component. Like this number here, I can represent it as a vector going from the origin to this point, and that vector has a horizontal part of 1 and a vertical part of 1. And so it's 1 plus 1i is the vector. And this is what we call Cartesian form. So it's the rectangular coordinate system. You also have the option of working in polar coordinates. Now, I know when polar coordinates get introduced in most problems, you're like, this is making my life harder instead of easier. Why are we doing this? I have good news. For complex numbers, working in polar form is often easier. Basically, if you're doing anything except addition, polar form is probably going to be easier. So looking at what we have here, here is my number. Here's my a plus bi, where I am going to write that. I want to convert it from Cartesian form, from real plus imaginary, to polar form. I want to write it in terms of a distance, r, from the origin, and an angle, theta, where that angle is the angle away from the real axis. Once you do this, you've got a triangle. So I've already got the sides labeled here, right? The base of the triangle is r cos theta. The height of the triangle is r sine theta. That's just all of your good old fashioned vector stuff and polar coordinates that you've seen before. So that means that instead of a plus bi, you could write this then as r cos theta plus r I sine theta. That's a plus bi. But you factor out the r, and so then that's r times cosine of stuff plus I times the sine of stuff. And that is something that I hope you remember at this point because I've made a big deal out of it in the past. Cosine plus I sine, that's e to the I theta. So this gives us our polar form for complex numbers. And this goes back to way, way back when I proved Euler's identity the first time with Taylor series in that case, by collecting like terms in the Taylor series and doing all that. I was like, there's other ways to prove this too. Here's another form of understanding that relationship. We're understanding that relationship just in terms of geometric properties of triangles in two dimensions. So we're saying that a rotation, e to the I theta, that is a rotation away from the real axis. And then you take that rotation and you scale it. Hey, look at me using the language of matrix transformations. You have a rotation factor, and then you have the scaling factor r, and that rotation plus that scaling takes you from the number 1 to the number r times e to the I theta. And that rotation and scaling are the hypotenuse and the angle of a triangle. So that brings us back to Euler's identity. Great. It all works. It all hangs together. Hello, Euler. So there it is, just to put it in not handwriting form so that you can read these things nicely. Now, when you start to do some math with these and we start adding and subtracting numbers, then this gives us some ways to look at different combinations of complex exponentials. So here, e to the I theta plus e to the negative I theta, you add these two things together, the I sine thetas cancel out, and you're left with a real number, 2 plus cos theta. So this combination of two numbers gives us a real value. And if we subtract them, then the real part cancels out and we're left with a purely imaginary value. Why is this significant? We'll see it come back soon. And that soon is now. So let me talk about the complex conjugate of a number. This was the thing I was saying. It's actually simple if you just get the recipe. Here's the recipe. If you have a complex number, a plus bi, its complex conjugate, you'll see it written two different ways. They're completely synonymous. Math people tend to more often write z bar like this. Physicists and other like science people, science engineering people tend to write z star. I personally use the z star notation because I use z bar for average, like for mean and statistics. So z star, the complex conjugate is, here's the recipe. The real part is the same. The imaginary part gets its sign, its positive or negative, sign, flipped. That's it. That's like actually the whole thing. I don't want to overcomplicate this. The properties of the conjugate are very interesting and can get complicated, and there's a lot to it. But how to calculate the conjugate of a number, you just flip the positive or the negative of the imaginary part. So in polar form, you leave r exactly the same because there's no I on that part, and then you flip the sign of the I. It goes from e to the I theta to e to the negative I theta. And so this, going back to the previous slide for a second, this was a number plus its conjugate, and that gave us some kind of real value. This was a number minus its conjugate, and that gave us some imaginary value. Okay, so let's do some algebra with these things. Addition and subtraction and multiplication are easy. You just treat these things as binomials. So if I've got two complex numbers, z and q, I wanted to use q because it never gets enough love as a variable. To add or subtract, you just collect like terms. The two real parts combine, that gives you the new real part here, and then the imaginary parts combine, and you get the new imaginary part here. That's it. That's addition and subtraction. When you multiply, again, you multiply like binomials, so you do first, outer, inner, last, and then you collect like terms. Notice that what happens here is we'll have this negative term at the end that comes from I squared, right? bi times di is b di squared, which is b times d times -1. So do be careful about that minus sign. That is just a common rookie mistake that people make when they get careless about their algebra. To find the notice I didn't say division, huh? To find the magnitude of a complex number, what you need to do is to take the conjugate of the number times the number. This gives us the square of the magnitude, and so then the magnitude itself is the square root of that. So writing this out in Cartesian form, we are going to have something really nice happen here, which is that we have plus ABI minus ABI. Those terms cancel out. And then I squared is real. We end up with a squared plus b squared. This is the Pythagorean theorem, which is consistent with Euler's identity because these things are vectors and triangles in a linear vector space. So how about polar form? How do you calculate the magnitude in polar form? It should work out the same. Oh, my bad. Weird. I guess I left out a slide. Sorry about that. Well, in polar form, the magnitude z is just the radius. That's it. Because when we do the conjugate times the original number, we have e to the plus I theta times e to the negative I theta, and those two things just cancel out. And all that's left behind is r. So, okay. When you want to take a complex number and raise it to an integer power, that just means multiply it by itself that many times. That's exactly the same as real numbers. And again, don't overthink it. When you want to take the exponential of a complex number, this one requires a little bit more thinking. It's not like super hard, but there's an extra step or two because thinking about how to evaluate e to the, I don't know, e to the 2 plus 3i, well, you would need to split that up because that e to the 2 plus 3i is e to the 2 times e to the 3i. This is one of the reasons that we reviewed properties of exponentials way back in the first day of class, was because they were going to come back later. Now it's later. And so then you have e to the 2, that would be the magnitude of your complex number, and then e to the 3i, that would be the angle part. It'd be theta equals 3. So it's 3 radians away from the real axis. What about other operations? I skipped division for a reason. It's because division's a pain in the ass. I'm just going to be honest about that. I'm going to make you do 1 or 2 division problems just for practice, and then we move on with our lives. This is the place where I said polar form is easier. Polar form makes your life simpler and better instead of worse. Because in polar form, everything just comes back to properties of exponentials. If you raise an exponential to a power, you know what to do with that. Raise an exponential to a complex power, you still know what to do with that, actually. So any of this kind of like exponentiation, logarithm stuff, anything like that, so much better in polar form. I still haven't talked about division. Let's just do a quick example or two to make this a little more concrete. So I've got 2 complex numbers here, 3 plus 4i and 1 plus 2i. What is their ratio? How do I divide 2 complex numbers? Well, division is the same as multiplication by the inverse. And you're like, really? We're playing that game? Yeah, sorry, we're playing that game. Because multiplication is defined. I showed you how to multiply complex numbers. So we need to know how to find the inverse of a complex number. How do we do that? Well, we go back to the definition of what an inverse is. The inverse is the number that when multiplied by the original number, that product is 1. So if z is 3 plus 4i, here's z, we need to solve for unknown values a and b such that this unknown complex number multiplied by the original number is 1 plus 0i. And you can do that. You do the multiplication and you get 2 equations and 2 variables. Solve this by whatever means you want. Kramer's rule is nice for 2 by 2, but as you see fit. And so then that gives you the real and imaginary components of z inverse. And so then you know z inverse. And then once you find that, then you multiply it by, in this example, q, and then you have finally done q divided by z. You're like, wow, that sucks. Yeah, it sucks. In Cartesian form. In polar form, it's not nearly as bad. So sorry, I forgot to animate this slide apparently, but the reason I chose 3 plus 4i is because it makes a nice little 3, 4, 5 triangle. It's like I feel like the 3, 4, 5 is my emotional support triangle. So I'm a big fan of that. Anyway, it's a 3, 4, 5 triangle. So the magnitude of z is 5. And then we need to find the angle. Well, the angle is arctan of 4/3 because our angle is here. And that means that you can just write z inverse immediately in polar form. it's got 1 over the magnitude, so 1/5 instead of 5, and the angle is the opposite. It's e to the negative I theta, because 1 over e to the x is e to the negative x. So there's our inverse. Wasn't that so much simpler than having to set up and solve a series of equations? And then we do the same thing with q. And so q is, its magnitude is square root of 5 because the base and the height are 1 and 2. And then the angle for q is arctan of 2. It's the arctan of y over x, so the imaginary part over the real part. And then you just multiply the two numbers and multiply. Oh my, wow, I'm done. Multiplying exponentials is easy. So there we go. So now you can divide. Congratulations. Or there's even other options. I mentioned this complex powers thing and I was like, hey, this isn't a big deal. Write it in polar form. The one clever step here, so I'm giving this away for free hint, r is e to the log r, right? Because exponentiation and logarithms are inverse functions of each other. So e to the log r is just r. And then once you've done that, then you can do your exponentiation business with properties of exponentials. This is e to the log r times e to the I theta, and then each of those is raised to, and you do your properties of exponentials. I know I'm rushing a little bit. It's not that I think this is unimportant. It's that it truly is use the rules of algebra that you already know. And you have these examples for reference. So if you need to spend some time with this to stop and think through it, absolutely do that. Okay, I did promise a little bit about vector spaces, and I want to wrap this up. So when we're in a complex valued vector space, the property I want to focus on for today is the inner product. There's one additional step to consider that makes this different from just the regular dot product. I think I teased this when I talked about dot products a couple weeks ago, so here it is. The inner product of complex valued vectors v and w is like the dot product, except the first vector, the one on the left, you have to take its complex conjugate. And the reason you have to take its complex conjugate is that inner products are always supposed to be positive, or zero if one of the vectors is the zero vector, because they represent the norm squared of a number. It is the length of the vector. It is the distance that that vector spans, and distances are positive things. See my little asterisk note. And if you're like, what does that mean? Well, we can talk in class. Uh, so because the lengths of vectors are positive, we need to define the inner product in a way that guarantees giving a positive result when we take the inner product of any vector with itself. And in order for that to be guaranteed positive, then it needs to be a complex conjugate for one of them. I do not have an example of that worked out here, but we'll see it on the homework. So if you have questions, you know where to ask them. Please do make sure to ask your questions in the check-ins. Even if it seems like a small thing, even if it's silly or dumb or like, oh, I feel like I should know this, just go ahead and ask it. Sometimes the mere act of writing out the question makes you think about it and then you figure it out yourself. And if it is a little thing and you just missed it, no big deal. I'm happy to help out. So send me those questions. Let me know what does and doesn't make sense. And before I sign out, I have to, of course, say why this matters. Everything to do with wave mechanics is much, much, much easier when you do it with complex numbers. Because instead of cosines and sines of everything and having to remember bizarre trig formulas like how to add sine of A plus sine of B, yeah, there's a trig identity for that. I don't remember it. It's gross. So instead of adding angles and doing terrible, terrible trig, just rewrite your angles as e to the I whatever. And it makes all the math so much better. Cannot recommend it enough. I'm not going to say more about that now because when we start doing applications of this and looking at complex numbers arising in different contexts over time, I think you'll see why this is actually a good way to do things. By the way, quantum mechanics is all built around complex vector spaces. So there it is. Okay, have a great day. I will see you next time.